The concept of optical activity is important in understanding enantiomers and the history of the discovery of enantiomers. John Baptiste Biot in 1832 observed the phenomenon of optical activity. He did this using solutions of tartaric acid, and we now know that optical activity is a property of chiral compounds, compounds having an enantiomer. Optically active compounds rotate plane polarized light. So let's remind ourselves what light is. It's electromagnetic radiation. It's a wave phenomenon where we have an electric field oscillating, and perpendicular to that is a magnetic field. So, optical activity utilizes plane polarized light. So, what is plane polarized light? Well, picture a light source that you're looking at, and there are photons of light coming towards you. If you have unpolarized light, the electric field vectors of each photon of light are arranged in no particular way. They could be at any particular angle as they come towards you. So one photon might have its electric field vector straight up and down, another one 90 degrees to that, or any particular angle. So you'll get the whole range of angles for the plane in which the electric field vectors lie. There's no particular plane that's favored, as is the case with plane polarized light, where all of the photons of light coming towards you have their electric fields in one plane. They're oriented in the same direction. So when we measure optical activity, like Biot did in the 19th century, we use what's called a polarimeter. And this involves polarizing light using a filter, a polarizer. You're familiar with these types of lenses with polarized sunglasses, for instance. So you have a light source, and electric field vectors are oriented randomly as they head toward the polarizer. The polarizer stops light that does not have the proper direction to pass through in regards to the electric field vector. So light having the correct electric field vector for the orientation of that polarizer passes through, the rest of the light is blocked, and now you have plane polarized light. This plane polarized light then passes through a solution containing the compound. This plane polarized light then exits the solution and passes through a second polarizer called the analyzer. Now that analyzer can be rotated, and you rotate it so that you observe the maximum intensity of light. If the light is not passing through, you rotate it until it becomes as bright as it possibly can. This angle, alpha, is the measurement of optical rotation. If you have to rotate clockwise, it is called dextrorotatory. It's symbolized with a plus or a D. If you have to rotate counterclockwise, it's levorotatory, negative or an L. So if you have an achiral compound An achiral compound is not optically active. You will observe no rotation of plane polarized light. So the angle is 0. Both polarizers will be oriented in the same direction because the plane polarized light produced by the first polarizer would not rotate, and so the second polarizer would have to be oriented in the same way. If you have a chiral compound, that is optically active. It will rotate plane polarized light. These terms, optically active and chiral, are actually interchangeable. If a molecule is chiral, it is optically active. If it's not chiral, it's not optically active. So these terms get interchanged and used synonymously. You rotate that analyzing filter until you observe the, the most intense passage of light through it. The angle relative to the first polarizer in which you have to rotate it is the measurement alpha. There is a term called specific rotation, and this is a calculated value from the measured rotation value. Optical rotation depends on the substance, but also on some experimental variables. So path length through the solution, how long the light travels through the sample solution, the solution temperature, the concentration, and the wavelength of light. Specific rotation is a calculated value that removes these experimental values. So the formula is as follows. We have the observed angle of rotation divided by the path length and also divided by the concentration. By dividing the angle measured by the path length and the concentration, this normalizes the angle to what it would be if the path length were 1 decimeter, 10 centimeters, and with a concentration of 1 gram per ml, 1 gram per cubic centimeter. That way you could compare different measured values without the concentration and the path length being a variable. Now the temperature and the wavelength are not corrected for in this calculation, but they're reported. So usually you make the measurement at a standard temperature, 25 degrees Celsius, and usually at a standard wavelength, 589 nanometers. So for instance, the specific rotation of camphor is 44.26 degrees, positive 44.26 degrees. And that is the specific rotation after having been calculated using this formula. And we're reporting that the temperature is 25 degrees, and for the wavelength, you'll see that capital D. Well, D is 589 nanometers. It's produced by excited vapor phase sodium atoms. The wavelength of light emitted from those atoms is very reproducible at 589 nanometers. So here you see tables with different specific rotations noted. Some are positive, dextrorotatory, some are negative, levorotatory. And it should be noted that specific rotation is a physical property that can be used to characterize a compound, just like melting point and boiling point and density. Now, what about enantiomers? If you have a chiral compound, you have its mirror image, its enantiomer. You have a pair of enantiomers. Well, both of them are chiral. Both of them are optically active, and they both have the same specific rotation in terms of magnitude, the angle. But the difference is that one will be dextrorotatory and one will be levorotatory. So if you know, for instance, that the specific rotation of a chiral compound is plus 30 degrees, what is the specific rotation of its enantiomer? It would be minus 30 degrees. Equal but opposite. So here's an example. If we take 2-butanol is a chiral compound, and we dissolve 6 grams of this into a solution with a total volume of 40 milliliters. We place this in a polarimeter with a path length of 200 millimeters, and we measure the optical rotation. We find that it's 4.05 degrees counterclockwise. So what is the specific rotation of this enantiomer of 2-butanol? Well, first of all, let's collect what we know about this. The angle of rotation, the optical angle of rotation is minus 4.05 degrees, and so it's levorotatory. We could name this minus 2-butanol to indicate which enantiomer it is. It's the negative levorotatory. The concentration is 6 grams divided by 40 milliliters. That gives us 0.15 grams per cubic centimeter. 200 millimeters is 20 centimeters or 2 decimeters. There's 10 centimeters in a decimeter. And so if we plug these values in and do the calculation, we get minus 13.5 degrees. What if you have mixtures? Like, in other words, both enantiomers are present in solution. Well, if you have both, one will rotate the light clockwise, one will rotate the light counterclockwise. So for instance, the specific rotation for one enantiomer might be plus 30 degrees. But you realize it may not be pure, some of the other enantiomer might be there. And so you measure the specific rotation and find that it's plus 25 degrees. What does that tell you? Well, the solution is not optically pure. You do not have only one enantiomer. What you actually have is mostly the dextrorotatory, but a little bit of the levorotatory, which rotates the light in the opposite direction and reduces the angle. So you can actually calculate optical purity from these measured values. So for instance, we could say the optical purity of this solution is 25 divided by 30 times 100, and we would find our optical purity. This is also called enantiomeric excess. It's another way to refer to this. Racemic mixtures are a special case. It is one in which you have a 50-50 mixture of enantiomers. This name is derived from racemic acid, that is a mixture of both enantiomers of tartaric acid. The mixture is also called a racemate. The net effect is no rotation of plane polarized light, because if it's a 50-50 mixture, each enantiomer is rotating the light an equal amount in opposite directions, and that cancels. The physical properties of racemic mixtures may also be different than pure enantiomers. And we can denote these racemic mixtures with a plus minus symbol. So that means 50-50 plus and minus, or D and L.